Silvanus Thompson. Elementary Lessons in Electricity and Magnetism. This book was written in 1895, so some ideas and units might be outdated, but its heritage value is great. All books on my channel are in public domain. Please, subscribe, like, and comment. Chapter 4. Electrostatics. Lesson 21. Theory of Potential. 259. By the lessons in Chapter 1, the student will have obtained some elementary notions upon the existence and measurement of definite quantities of electricity. In the present lesson, which is both one of the hardest and one of the most important to the beginner, and which he must therefore study the more carefully, the laws which concern the magnitude of electrical quantities and their measurement are more fully explained. In no branch of knowledge is it more true than in electricity. That science is measurement. That part of the science of electricity which deals with the measurement of charges of electricity is called electrostatics. We shall begin by discussing first the simple laws of electric force, which were brought to light in Chapter 1, by simple experimental means. 260. First law of electrostatics. Electric charges of similar sign repel one another, but electric charges of opposite signs attract one another. The fundamental facts expressed in this law were fully explained in Lesson 1. Though familiar to the student, and apparently simple, these facts require for their complete explanation the aid of advanced mathematical analysis. They will here be treated as simple facts of observation. 261. Second law of electrostatics. The force exerted between two charges of electricity, supposing them to be collected at points or on two small spheres, is directly proportional to their product, and inversely proportional to the square of the distance between them. This law, discovered by Coulomb and called Coulomb's law, was briefly alluded to, on page 21, in the account of experiments made with the torsion balance. And examples were there given in illustration of both parts of the law. We saw, too, that a similar law held good for the forces exerted between two magnetic point poles. Coulomb applied also the method of oscillations to verify the indications of the torsion balance and found the results entirely confirmed. We may express the two clauses of Coulomb's law in the following symbolic manner. Let F stand for the force, Q for the quantity of electricity in one of the two charges, and Q' for that of the other charge, and let R stand for the distance between them. Then, 1 F is proportional to Q times Q', and 2 F is proportional to 1 over R squared. These two expressions may be combined into one. And it is most convenient so to choose our units or standards of measurement that we may write our symbols as an equation. F equals charge Q times charge Q' over R squared. 262. Unit of electric quantity. If we are, however, to write this as an equality, it is clear that we must choose our unit of electricity in accordance with the units already fixed for measuring force and distance. Electricians of all nations have agreed on adopting a system which is based upon three fundamental units, that is, the centimeter for a unit of length, the gram for a unit of mass, the second for a unit of time. All other units can be derived from these, as is explained in the note at the end of this lesson. Now, amongst the derived units of this system is the unit of force, named the dyne, which is that force which, acting for 1 second on a mass of 1 gram, imparts to it a velocity of 1 centimeter per second. Taking the dyne then as the unit of force, and the centimeter as the unit of length, or distance, we must find a unit of electric quantity to agree with these in our equation. It is quite clear that if Q, Q', and R were each made equal to 1, that is, if we took two charges of value 1 each, and placed them 1 centimeter apart, the value of Q times Q' over R squared would be 1 times 1 over 1 times 1, which is equal to 1. Hence we adopt, as our definition of a unit of electricity, the following, which we briefly gave at the end of Lesson 2. 1 unit of electricity is that quantity which, when placed at a distance of 1 centimeter, in air from a similar and equal quantity, repels it with the force of 1 dyne. An example will aid the student to understand the application of Coulomb's law. Two small spheres, charged respectively with 6 units and 8 units of plus electricity, are placed 4 centimeters apart. Find what force they exert on one another. By the formula, F equals Q times Q' over R squared, we find F equals 6 times 8 over 4 square equals 48 over 16, equals 3 dynes. Note below, in reference to the above, that is 1 unit in the electrostatic system. It is only 1 over 300th million. The force in the above example would clearly be a force of repulsion. Had one of these charges been negative, the product Q times Q' would have had a negative value, and the answer would have come out as minus 3 dynes. The presence of the negative sign, therefore, prefixed to a force, will indicate that it is a force of attraction, whilst the plus sign would signify a force of repulsion. The intensity of an electric field, Article 266, being measured by the force it exerts on a unit charge. It at once follows that at a distance of r in air from a charge Q, the intensity of the electric field due to that charge will be Q over R squared. If the intervening medium be not air, but have a specific dielectric capacity, K, the the field will be only Q over kr squared. 263. Potential. We must next define the term potential, as applied to electric forces, but to make the meaning plain a little preliminary explanation is necessary. Suppose we had a plus charge on a small insulated sphere A, see figure 144, placed by itself far from all other electric charges and conductors. If we were to bring another positively charged body, B, near it, A would repel B, but the repelling force would depend on the quantity of the new charge, and on the distance at which it was placed. Suppose the new charge thus brought near to be 1 plus unit. When B was a long way off, it would be repelled with a very slight force, and very little work need be expended in bringing it up nearer against the repelling forces exerted by A. But as B was brought nearer and nearer to A, the repelling force would grow greater and greater, and more work would have to be done against these opposing forces in bringing up B. Suppose that we had begun at an infinite distance away, and that we pushed up our little test charge B from B' to B double prime and then to Q, and so finally moved it up to the point P. Against the opposing forces exerted by A, we should have had to spend a certain amount of work. That work represents the potential at the point P due to A. For the following is the definition of electric potential. The potential at any point is the work that must be spent upon a unit of positive electricity in bringing it up to that point from an infinite distance. Had the charge on A been a minus charge, the force would have been one of attraction, in which case we should have theoretically to measure the potential at P, either by the opposite process of placing there a plus unit, and then removing it to an infinite distance against the attractive forces, or else by measuring the amount of work which would be done by a plus unit in being attracted up to P from an infinite distance. It can be shown that where there are more electrified bodies than one to be considered, the potential due to them at any point is the sum of the potentials, at that point, of each on taken separately. It can also be shown that the potential at a point P, near an electrified particle A, is equal to the quantity of electricity at A divided by the distance between A and P. Or, if the quantity be called Q, and the distance is R, the potential is Q divided by the distance, R. Proof. First determine the difference of potential between point P and point Q done to a charge of electricity G on a small sphere at A. Call distance AP equals R, and AQ equals R prime. Then PQ equals R prime minus R. The difference of potential between Q and P is the work done in moving a plus unit from Q to P against the force, and since work equals average force times distance through which it is overcome, V of P minus V of Q equals F brackets, R prime minus R. Prime minus R. Force at P exerted by Q on a plus unit equals Q over R squared. And the force at Q exerted by Q on a plus unit equals Q over R prime squared. Suppose now that the distance PQ be divided into any number of equal parts, R to R1 and R1 to R2 and so on. And so, R subscript n-1 times R prime. The force at R equals Q over R squared. And the force at R1 equals Q over R1 squared, etc. Now since R1 may be made as close to R as we choose, if we only take an n a large enough number, we shall commit no serious error in supposing that R times R1 is a fair mean between R squared and R squared prime. Hence we may assume the average force over the short length QR to R1 be Q over R time R1. Hence the work done in passing from R1 to R will be Q divided by R times R1 brackets R1 minus R equals Q brackets 1 over R minus 1 divided by R1. On a similar assumption, the work done in passing from R2 to R1 will be calculated in the way shown on the screen, giving us by R1. On a similar assumption, the work done in passing from R2 to R1 will be calculated in the way shown on the screen, giving us n equations, of which the last will be the work done in passing from R prime to R with a subscript n-1. Equation is shown on the screen. Adding up all these portions of the work, the intermediate values of R cancel out, and we get for the work done in passing from Q to P, P of P minus V of Q equals Q brackets 1 divided by R minus 1 divided by R prime. Next suppose Q to be an infinite distance from A. Here R prime equals infinity, and 1 over R prime equals 0. In that case the equation becomes V of P equals Q over R. If there are a number of electrified particles at different distances from P, the separate values of the potential Q over R due to each electrified particle separately can be found, and therefore the potential at P can be found by dividing the quantity of each charge by its distance from the point P and then adding up together the separate amounts so obtained. The symbol V is generally used to represent potential. The potential at P we will call V of P, then V of R equals Q prime over a prime plus Q double prime over a double R prime etc., or V of P sigma Q over R. This expression sigma Q divided by R represents the work done on, or by a unit of plus electricity when moved up to the given point P from an infinite distance, according as the potential at P is positive or negative. 264. Zero potential. At a place infinitely distant from all electrified bodies there would be no electric forces and the potential would be zero. For purposes of convenience it is, however, usual to consider the potential of the Earth as an arbitrary zero. Just as it is convenient to consider sea level as a zero from which to measure heights or depths. 265. Difference of potentials. Since potential represents the work that must be done on a plus unit in bringing it up from an infinite distance, the difference of potential between 2 points is the work to be done on a plus unit of electricity in carrying it from one point to the other. Thus if V of P represents the potential at P, and V of Q the potential at another point Q, the difference of potentials V of P minus V of Q denotes the work done in moving up the plus unit from Q to P. It is to be noted that since this value depends only on the values of the potential at P and at Q, and not on the values at intermediate points, the work done will be the same, whatever the path along which the particle moves from Q to P. In the same way it is true that the expenditure of energy in lifting a pound, against the Earth's attraction, from one point to another on a higher level, will be the same whatever the path along which the pound is lifted. 266. Electric force. The definition of work is the product of the force overcome into the distance through which the force is overcome, or work equals force times distance through which it is overcome. Hence, if the difference of potential between 2 points is the work done in moving up our plus unit from one point to the other, it follows that the average electric force between those points will be found by dividing the work so done by the distance between the points. Or V of P minus V of Q over P times Q equals F, which is the average electric force along the line PQ. The average electric force is therefore the rate of change of potential per unit of length. If P and Q are near together the force will be practically uniform between P and Q. The term electromotive intensity is sometimes used for the force in an electric field. We may represent this intensity of the electric field by supposing the number of electric lines per square centimeter to be drawn to represent the number of dynes of force on a plus unit placed at the point. 267. Equipotential surfaces. A charge of electricity collected on a small sphere acts on external bodies as if the charge were all collected into one point at its center. We have seen that the force exerted by such a charge falls off at a distance from the ball, the force becoming less and less as the square of the distance increases. But the force is the same in amount at all points equally distant from the small charged sphere. And the potential is the same at all points that are equally distant from the charged sphere. If, in figure 145, the point A represents the sphere charged with Q units of electricity, then the potential at P, which we will call V of P, will be equal to Q over R1 where R is the distance from A to P. But if we take any other point at the same distance from A, its potential will also be Q over R. Now all the points that are the same distance from A as P will be found to lie upon the surface of a sphere whose center is at A, and which is represented by the circle drawn through P, in figure 146. All round this circle the potential will have equal values, hence this circle represents an equipotential surface. The work to be done in bringing up a plus unit from an infinite distance will be the same, no matter what point of this equipotential surface it is brought to. And to move it about from one point to another in the equipotential surface requires no further overcoming of the electrical forces, and involves therefore no further expenditure of work. At another distance, say at the point Q, the potential will have another value, and through this point Q another equipotential surface may be drawn. Suppose we chose Q so far from P that to push up a unit of plus electricity against the repelling force of A required the expenditure of just 1 erg of work. For the definition of 1 erg see the note on units at the end of this lesson. There will be then unit difference of potential between the surface drawn through Q and that drawn through P, and it will require 1 erg of work to carry a plus unit from any point on the one surface to any point on the other. In like manner we might construct a whole system of equipotential surfaces about the point A, choosing them at such distances that there should be unit difference of potential between each one and the next. The widths between them would get wider and wider, for, since the force falls off as you go further from A, you must, in doing 1 erg of work, Bring up the plus unit through a longer distance against the weaker opposing force. The form of the equipotential surfaces about two small electrified bodies placed near to one another would not be spherical. And around a number of electrified bodies placed near to one another, the equipotential surfaces would be highly complex in form. 268. Lines of force. The electric force, whether of attraction or repulsion, always acts across the equipotential surfaces in a direction normal to the surface. The lines which mark the direction of the resultant electric forces are sometimes called lines of electric force. In the case of the single electrified sphere, the lines of force would be straight lines, radii of the system of equipotential spheres. In general, however, lines of force are curved. In this case, the resultant force at any point would be in the direction of the tangent to the curve at that point. Two lines of force cannot cut one another, for it is impossible. The resultant force at a point cannot act in two directions at once. The positive direction along a line of force is that direction in which a small positively charged body would be impelled by the electric force if free to move. A space bounded by a number of lines of force is sometimes spoken of as a tube of force. All the space, for example, round a small insulated electrified sphere may be regarded as mapped out into a number of conical tubes, each having their apex at the center of the sphere. The total electric force exerted across any section of a tube of force is constant wherever the section be taken. 269. Potential within a closed conductor. The experiments related in articles 32 to 36 prove most convincingly that there is no electric force inside a closed conductor due to charges outside or on the surface of the conductor. Now we have shown above that electric force is the rate of change of potential per unit of length. If there is no electric force, there is no change of potential. The potential within a closed conductor, for example, a hollow sphere, due to charges outside or on the surface, is therefore the same all over the interior, the same as the potential of the surface. The surface of a closed conductor is necessarily an equipotential surface. If it were not at one potential, there would be a flow of electricity from the higher potential to the lower, which would instantaneously establish equilibrium and reduce the whole to one potential. The student should clearly distinguish between the surface density at a point and the potential at that point due to neighboring charges of electricity. We know that when an electrified body is placed near an insulated conductor, the nearer and farther portions of that conductor exhibit induced charges of opposite kinds. Yet all is at one potential. If the plus and minus charges on the conductor had not separated by a movement of electricity from one side to the other, a difference of potential would exist between those sides because they are at different distances from the electrified body. But that is a state of affairs which could not continue in the conductor. For the difference of potential would cause electricity to flow, until the combined potential due to the electrified body and the charges at the opposite sides was the same at every point in the conductor. The potential at any point in a conducting sphere, hollow or solid, due to an electrified particle A, situated at a point outside, figure 148, is equal to the quantity of electricity Q at A divided by the distance between A and the center of the sphere. For if B be the center of the sphere, the potential at B due to Q is Q over R, where R equals AB. But all points in the sphere are at the same potential, therefore they are all at the potential Q over R. The Earth is a large conducting sphere. Its potential, due to a positive charge Q near to its surface, is Q over R, where R may be taken as the radius of the Earth, that is 636,000 centimeters. But it is impossible to produce a plus charge Q without generating also an equal negative charge minus Q. So the potential of the Earth due to both charges